Mia? Am I here?
Hi.
What's going on, Brandon? For nice to see everybody. People I don't usually get to see a lot of times. What's going on, people? So people that didn't come to class, the people that couldn't come to the lecture today, don't even know the drama with the light setup. I mean, look, check this out. I got this brand new light. I was so excited about it. But then, what did I just do? I was so excited about it. So this is the old light setup. Like you know, it works. Like you can see, it's fine. A little cumbersome for me, but it works. So I got this new light. Wait a minute.
It looks similar.
Alfred, do you see the little lines again?
This is so much better than the class. Because now it's not even blur and there's no sort of like different sort of lighting because you could see like horizontal lines going up or down that time.
I didn't change anything. Wait a minute. This is fascinating. I almost went and bought a new light, but I don't have to buy a new light. This is a good thing.
Hey, Prof.
Hi.
Do you have you considered like Khan Academy style tablet kind of thing on the screen?
I have.
Infinite whiteboard.
I have, and there's definitely advantages to the infinite whiteboard, but I hate it.
Really?
And I'll tell you why I hate it. And this is like a totally weirdly artistic, like stylistic choice, and that is I really like the idea of you can see my hands, I can gesture with my hands, like I can point things here and here and stuff like that. And it feels much more personal in person. And maybe it's foolish in the sense that this is me online trying to strive to create the most in-person atmosphere, but maybe I'm not taking advantage of online because then now that you're online, you don't have to do in person, so you can do different things. Maybe you can do things that you couldn't do in person. But I did teach a class in the summer that where I did Khan Academy, more Khan Academy style, and I just didn't like it. I just didn't like it. It felt even less personal than this. I don't know how personal this feels to you, but it feels pretty personal. Like you guys are in my apartment right now, virtually. So
I like your tool thing.
my pickboard.
Yeah.
Thank you very much. Yeah. I don't know if you guys remember at like the very first class on the ground because I bought a bunch of wood. I was like, I can build a desk in a weekend. Turns out I couldn't, so I was doing it on the ground. But I mean, you guys can't really see progress that's been made. I mean, we got an L, we got that, we got a book. Like it's pretty substantial. It only took like 10 weeks.
Good looks. Good looks.
Thank you. Well, Afra, this is fantastic news that the light's not screwing up anymore. The glare's probably still there. Yeah, but that's easier to fix. Interesting. Well, it's late. So who's got questions?
I have questions from the written assignments.
Yeah, sure. Which ones? Wait, do you know which ones?
Yeah. Written assignment 8, number 2.
How's that go? I wish I was a savant and knew that.
This was the one that the question was to contradict the claim that the gardener is not the murderer.
Oh, yes. This one's good. Okay, so this one, I'm not really gonna write anything down. I'm just gonna. Oh, we got chat too. I leave a little bit, but for me, excuse me in advance. Would it be possible to upload this one session over? It is Mahir. That's why I am recording. But actually, Mahir, if you have to leave in a little bit, what's your question? Maybe we could do that real quick before the Gardner question. That's okay.
I don't have any specific questions. I just want to pop in, see what people are asking, maybe listen.
Perfect. Cool. So the Gardner question, I personally liked it. I think it's my favorite homework question we've had so far. Oh, you guys don't want to see the exam, do you? That'd be embarrassing. Yeah, you guys can see this now. So let's share screen. All right. Let's go to assignments. Hello there, Afra. And so you probably think there's some kind of special way that I access this stuff as a teacher, but I don't. It's just like the same way you guys do. Here we go. So the question is, there's been a murder, and so ask mathematicians to help solve it. The crime took place at the old haunted mansion owned by a titan of industry, Miss Carol Asper, which is C. Asper, like Casper. I'm clever. And her husband. Carol was the victim. Here are the indisputable facts according to Scotland Yard. Apparently it's in London. The crime took place in the milk cellar. I had fun with this one, you can tell. There are only two beings in the cellar at the time of the crime, the victim and the assailant. If the housekeeper says exorcist was in the room at the time of the crime scene would not be dirty. The butler was away on holiday. If the gardener was the murderer, there'd be a dirt at the crime scene. The housekeeper says exorcist was not in the cellar, then the evil ghost, Wyatt Sheep, would be there. So, here's the deal. The idea with contradiction is like the reason I get so excited about it personally is not because it really has anything to do with math. It's because contradiction, like we're talking about, like with the lawyer examples and things like that, and with these examples of like murder mystery examples, contradiction is that cool stuff you see in like detective movies and lawyer movies and things like that. It's the idea of somehow sussing out what happened with what feels to be too little evidence. I mean, that's what we love about detective movies, is that like Sherlock Holmes, right, can use these like three things that seem unrelated and put them together and all of a sudden deduce something that no one else saw. But that's what we can do with math. I wanted to bring it out of the world of math for a second to help you guys see it. Hopefully, I hope you guys had fun with it. And that is this question right here, what's kind of like a murder mystery. Actually, it's exactly is a murder mystery question. And so the beautiful idea of contradiction is rather than trying to prove something true, let's try to prove something false. And that seems like it should be just as hard, but it's actually not. So here's the deal. The way that we're going to prove that the gardener was not the murderer is to assume he is the murderer and then prove that that has to lead to some kind of weird contradiction. So here's the idea. The idea is to start off by assuming the gardener is the murderer, right? So we start assuming the gardener is the murderer. And by E, if the gardener was the murderer, there'd be dirt at the crime scene. So since we're assuming the gardener did it, that means there must be dirt at the crime scene. But by C, if the housekeeper says exorcist was in the room at the time of crime, the crime scene would not be dirty. So Afra, what's that tell us about the housekeeper?
That he cleaned after the murder.
Yeah, I mean, that's true. Actually, that's a good way to put it. But what I'm getting at more is that if the gardener was the murderer, there'd be dirt at the crime scene. And since the dirt was at the crime scene, could the housekeeper have been in the room? Because if the housekeeper was in the room, the crime scene wouldn't be dirty. So since the crime scene was dirty, assuming the gardener did it, then that means the housekeeper couldn't have been there. And then this is by contrapositive. So the contrapositive to the housekeeper was in the room at the time of the crime scene would not be dirty. The contrapositive to that is that if the crime scene was dirty, the housekeepers as exorcists could not have been in the room at the time of the crime. They cleanse souls and houses. The point being, if we assume the gardener did it, then the crime scene would be dirty, and the housekeeper would not be there. But if the housekeeper says exorcist was not in the cellar, then the evil ghost, Wyatt Sheet, would be there. So by F, that means since we know the housekeeper wasn't there, the ghost would be there. So because if we assume the gardener was the murderer, their crime scene would be dirty, so the housekeeper would not be in the cellar, and so therefore the ghost would be there. But who else was in the crime? But who else was in the cellar at the time of the crime? Who had to be there?
The victim.
The victim, right? The one person that has to be at every murder scene is the victim, sadly. And so the victim, Carol Asper, had to be there. So that means that if the gardener was the murderer, he was there. But since the housekeeper couldn't have been there, Wyatt Sheet was there. But then also the victim, Carol, would have been there. So that means there's three beings, maybe not people, because I don't know how ghosts are kind of legally. I don't think they can vote. There's three people in the crime scene at the time of the crime. But by B, for some reason, there's some evidence that supports that there are only two beings at the cellar at the time of the crime: the victim and the assailant. There's only two souls present. So what that means, well, that's a contradiction. That means that if we know that these 1, 2, 3, 4, 5, 6, F's the sixth letter. If we know these 6 things are true, and we try to also say the gardener is not the murderer, well, they start to contradict each other. The gardener being the murderer doesn't gel with these 6 things. Now, that doesn't mean that we know who the murderer is. That doesn't mean, oh, the murderer is the housekeeper. We don't know anything about who actually did it. We just know the gardener couldn't have done it. Because if he did do it, then one of these has to be wrong because they don't play together. Either the victim, either maybe there are actually 3 people there. So either B is wrong, or maybe C is wrong, or maybe F's wrong. But one of those has to be wrong for the gardener being the murderer to make sense. But the evidence supports, but we're told these are correct. These are facts. We're told these are right. And so that means that the gardener could not have been the murderer, because if he was, it would lead to a contradiction. How's that?
I had a hard time contradicting the facts. So that
Yes. So yes, exactly. Now, in mathematical contradiction, right? We could make a bunch of assumptions, and then kind of the same thing, right? We make a bunch of assumptions, and then eventually those lead to a contradiction. If those lead to a contradiction, that means that your assumption has to be wrong. So you make some assumption like there's some real number, or like there's some rational number that equals the square root of 2, something like that. You make that assumption and show that a contradiction comes from that. So therefore your assumption had to be wrong. Same idea. Why is this light off? Yay. What's next? Who's got another question? Any more things on homework? Connor, hello. What people streaming in? We just went over the oh, perfect. I think you're connected to audio, so you can't talk, but I can talk to you. Perfect. That's how's it going, Connor? We're talking about the gardener example. I hope everyone liked that. And now we're saying, does anyone have any more homework questions or anything that they were a little iffy on and would like to see done again and explained fully?
Have you already shown number 2 from last night's homework?
No?
Could you show that?
Absolutely. Let's check it out. So let me see here. So number 2. Oh, I didn't change the Canvas webpage. I'll do that tonight. So yeah. So number 2 says, Prove the following claim. Yes. All right.
I solved it mathematically, as in like
The telescoping.
I proved it using math.
Like was it kind of like you said that? So the claim. Don't do this to me, camera. See, I'm experimenting with this too. Is this back? Timeout. Timeout. New markers. So this one is a question, it's a summation question. And you could do it theoretically, not even theoretically, you just could do it using like telescoping series things you might learn in calculus. Oh, night and day. Night and day if this back. I don't know why webcam's screwing up all of a sudden. There we go. So the claim is for all n greater than or equal to 1, for all integer n greater than or equal to 1. So I guess really you want to say for all n in the set of x and z such that x is greater than or equal to 1. The summation from k equals 1 to n of what was it? 1 over k times k plus 1?
Yep.
Yeah. That equals, what was it? 1 minus 1 over
N plus 1.
n plus 1. So this is the claim. Oh, see, the lines are back. You see that? Interesting. Okay, well, we're not gonna screw this now. I'll screw this alone. Let's screw this later. By myself. Much harsher. So, just feels less bright in here. But anyway, is the claim, and you could prove this using telescoping things about math. If you guys remember that from calculus, but we're just gonna skip that for now because we're on a budget of time here. And let's talk about how you prove this using weak induction. So the proof using weak induction would go sound like this. You'd say proof, and like always, you say proof by weak mathematical induction, like that. And then you have a base case, you have an inductive step. And the great thing about weak induction is that you're always only going to have one base case. In strong induction, you might need multiple base cases depending on what your inductive step needs. But here, we only need one base case, so it's really easy. So the base case has to be the first one in our set we say it works for. Since we're saying this works for all integers greater than or equal to 1, we're going to start at 1, and equal 1. And then the idea by induction is you want to try to show the claim is true for, we're trying to show that the claim is true for n equals 1 for the base case, and then show that then the domino effect takes over, that whole thing. So for n equals 1, so this claim is true. The claim that this sum equals 1 minus 1 over n plus 1. So we're going to say note the sum from k equals 1. So since n equals 1, actually I'll just keep it like that, of k times k plus 1. Plugging in 1, this is the sum from k equals 1 to n of, n's 1. So now we're plugging in 1, so sum of 1 to 1 of 1 over k times k plus 1. But the sum ranging from 1 to 1, that's just the one thing. It just has one term. It's where you put the 1 in. So this is 1 over 1 times 1 plus 1. And then normally we'd go like 2 over 2 times 2 plus 1, which is to stop at 1. So we just stop at this one term. So it's not really much of a sum. But the point is, this equals 1 over 1 times 2, which equals 1/2. Now the claim isn't that this sum equals 1/2, it's that it equals 1 minus 1 over n plus 1. So now I have to see what 1 minus 1 over n plus 1 is. So I'll say further, note 1 minus 1 over n plus 1, since n equals 1, this is 1 minus 1 over 1 plus 1, this is 1 minus 1/2, and 1 minus 1/2 is of course 1/2. So 1/2 equals 1/2. Thus, summation of k equals 1 to 1 equals 1 minus 1 over 1 plus 1, or I'll use n's here. 1 over k times k plus 1 equals 1 minus 1 over n plus 1. So the base case holds. So here we're just verifying that this is in fact true if n equals 1. It took 3 lines weirdly. I thought it'd be quicker. I don't know why it took me so long to do that. But yeah. So next is the inductive step. And the inductive step is interesting. So here in the inductive step, right, this is where, I'll use blue. This is where we want to show that for all n greater than or equal to 1, P of n implies P of n plus 1. That's the idea of the inductive step. Because this is like saying that one domino will knock over the next domino. If we know that every domino will knock over the next domino, that's what this is, then that's our chain reaction right there. We just knock one down, and then we'll know for a fact the rest will fall over. So this is the chain reaction thing that makes induction beautiful. This is what we have to prove. Now that we know it works for one will fall down, we have to show that the rest will fall down after that. That's what this does. So again, in terms of our problem, we want to show that for all n greater than or equal to 1, if the summation, the sum from k equals 1 to n of 1 over k times k plus 1 equals 1 over 1 minus, no, I don't want that. That would be too complicated. 1 minus 1 over n plus 1. So if the claim is true for n, that's P of n, then we want the claim to be true for the next one. So it works for n, let's show it works for n plus 1. Because then if it works for n plus 1, or for n plus 2, or for n plus 2, or for n plus 3, on. That's the chain reaction that proves it for everything. So then let's look at, so then now we want to show that the summation from k equals 1 to n plus 1 of 1 over k times k plus 1. We want to show that that will in fact equal what we want it to, which here would be 1 minus 1 over, now this n right here refers to this right here. So if we're plugging n plus 1 in here now, we want to put an n plus 1 in here. You kind of see what I'm saying? I'm just saying if this form holds for n, I want to prove it'll hold for n plus 1. So how can we do that proof is the question. So, well, let's get to thinking, right? This might not be, I'm switching out my new markers. Yeah, let's do an aside. Let's see what we're thinking about here. So let's look at this sum from k equals 1 to n plus 1 of 1 over k times k plus 1. This is what we want to equal 1 minus 1 over n plus 2 eventually. And we're working with the knowledge. We're going to assume, we get to assume this part's true. That the sum from 1 over k to k plus 1 works equally 1. So the question is, yeah, how can we use knowledge we have here to help prove something here? Like what I'm really asking is, how does this sum relate to this sum? How do we get from this sum to this sum? They look really similar, right? What's the one difference between these two sums?
The last value.
Yeah. This goes up to n. This goes up to n plus 1. So this sums everything from 1 to n, all this stuff. This is everything to 1 to n plus 1, all this stuff. So this is really equal to the sum from 1 to n of 1 over k times k plus 1 plus the very last term, 1 over n plus 1 times n plus 1 plus 1. Because this is the sum of everything from 1 to n plus 1. So that means it's the sum of everything from 1 to n plus that last n plus 1 bit. Does this make sense? Do you see what I'm saying here?
Yep.
Good, 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 good. And that's all we need, because then we know this guy right here, well, we're assuming that we're assuming it holds for n. We're trying to prove it holds for, it also holds for n plus 1. So assuming it holds for n, well, it's just going to be equal to 1 minus 1 over n plus 1. And then we still need to add this guy, which is 1 over n plus 1. N plus 1 plus 1 is n plus 2. Aha, now it's just to work with. So now it's going to be 1. Oh, you can't see that. Now it's going to be 1 minus, I'm going to factor out, yeah. I'll factor out an n plus 1, 1 over n plus 1. So this is going to be 1. I mean, actually, let's just get common denominators here, right? So this is going to be minus 1 over n plus 1 times n plus 2 over n plus 2, right? Plus 1 over n plus 1 times n plus 2. Sorry, then we do a little more math. We get down to this equals 1 minus, now I have common denominators. So actually this is plus minus n plus 2 plus 1 over n plus 1 times n plus 2. Which of course, this is going to equal 1 plus, so the minus n comes out, minus 2 plus 1. But minus 2 plus 1, that's just minus 1, right? Over n plus 1 times n plus 2, which we factor out the negative. That's 1 minus n plus 1 over n plus 1 times n plus 2. But then we're going, because that goes away, so we get 1 minus 1 over n plus 2. So that's the idea. The idea, does anyone want to see like the actual formal totally written up proof? It's basically just this, but you say up top, you say let n be an arbitrary of a particular integer greater than or equal to 1. Then you assume that this equation is true. The sum from k equals 1 to n of this equals 1 minus 1 over n plus 1. And then you do this exact math to get down to here. And then you go, oh, that's what you wanted to prove. So you go, therefore, the conclusion is therefore for all n equal to 1, this holds. Does anyone want to see that? Because I'm happy to do it, but how much time do we have left? What time is it? We have half an hour left. Okay, well, what do you guys want to see next then? Connor, did this help though?
Yeah. Could I see another weak induction example though?
Yeah. Sure. And I'm gonna use
Start or how to like set up 3 from the homework. Because it's similar to the one from class, but like it has like 2 more facts.
yeah, it's got a lot, yeah. The form is similar, but it's got a lot more going on. It has a lot more going on. This is what I get for experimenting. There we go. Back to the standard setup. So, the claim, if you guys remember the one that from homework 10, number 3. The claim is that for all X and D, X has green eyes. And then this is where D, this is the Valvo family tree. And actually get it up so we can look at the facts. Let's share screen. Yeah. So here's the problem we're looking at. Look at number 3. And number 3 starts with this weird family tree where the Valvo family tree that we care about is all maroon here. And then note that D0 is set up just Daniel Valvo, D1 is set Daniel Valvo's children, D2 is Daniel Valvo's grandchildren, D3 is Daniel Valvo's great-grandchildren, etc. So with D being the set of all Daniel Valvo's descendants, including Daniel Valvo, all the maroon circles above. So D is just the maroon. The orange people married into the family, but we don't care about them too much. So, and there's a few things to notice about this setup here. And that is that clearly for all X and D that are not Daniel Valvo, or for all X and D, if X is in DN, so if it's kind of in the nth generation, well, the parent, then their children will be in the n+1 generation. That's just how generations work, right? So these guys in D1, their kids will be in D2. And then the opposite for children of parents, right? So if you're anybody in here except for me, because my parents don't show up in this family tree, but I do have parents. I'm not some kind of divine birth. If you're not me, then you're somewhere down here in the tree, and that means that your parents are in the generation above. So if you're any one of these maroon circles in this tree and you're not me, Daniel Valvo, that means that you have a parent also in D and then generation above. So if you're in D and your parents are in D and -1. So that's the way this family tree works. And we have 3 facts. We're saying that for all X and D, if X is from the northern hemisphere, then X will marry someone from the southern hemisphere. And we also know for all X and D, if X is a parent from the southern hemisphere and X is a pair of green eyes, then X will have green eyes. This is genetics. I don't make it up. It's just whatever it is. I don't make the rules. In fact, C. Daniel Valvo from the United States has green eyes. Both kind of true. Green, brown, whatever. So the point is, these are the facts we have. And so let's see how we can put these together to do an inductive proof. So the base case is always simple. And so the idea is to do an inductive proof on the generations, because generations are kind of like textbook inductive things in the sense that each generation is generated from the previous generation, right? Like my parents' generation generated me, and then I'll generate my kids' generation. They'll generate the grandkids. Like they each generate the next generation. This generating, this self-generation thing is exactly what induction and recursion is. They're very, very, very related. So I think that's like generation, regenerate. Anyway, the point is, I never thought about that. Generating generation. The point is, this is just right for an inductive proof. So if we proof, now let's say proof by weak induction on N. So the idea here is that we'll do induction on the generations, basically saying that if everyone in this generation has green eyes, everyone in the next generation must have green eyes, and then if we can prove that link, well then it's going to be true because it starts with Daniel Valvo, it's got green eyes. So the base case goes like this. So for all x in D, x has green eyes. What this is really equivalent to is the saying for all n greater than or equal to 0, well, we should really have for all n in x and that and x in z such that x greater than or equal to 0, just to be nice and yeah. If you have this as a fact, or sorry, for all n in this set right here, so for all n greater than or equal to 0, we want to prove that for all x in Dn, x has green eyes. These two things are saying the same thing, right? Because D is my entire family tree. It's just made up of all these generations. So if we can prove that everybody in every generation has green eyes, well, then everybody in my family tree has green eyes. That's all it's saying. So we're breaking it up by generations. And so the base case is the first generation, the 0th generation. That's me. And so the base case is let n equals 0. Hopefully that'll come back in a second. There we go. Let n equals 0. Then, for x green eyes. Yeah. So let n equals 0. Then note D0 has one person in it. That's Daniel Valvo. Now, by fact C, Daniel Valvo has green eyes. Thus, every person in Dn where n equals 0 has green eyes. So that's the base case. We've proven that everyone in the 0th generation has green eyes. Now what I want to do is show that if this claim is true for n, it'll be true for n plus 1. If everyone in the nth generation has green eyes, everyone in the n plus 1 generation will also have green eyes. So we have our inductive step. There we go. And so here we want to show that for all n greater than or equal to 0, P of n implies P of n plus 1. That's the chain we want to show. This is the little link of the chain we want to show. And a particular problem with this is saying for all n greater than or equal to 0, if for all x, for all y, and Dn, I'll put it like this. If every y in Dn has green eyes, then every x in Dn plus 1 has green eyes. So try to show that if everyone in Dn has green eyes, then everyone in Dn plus 1 will also have green eyes. Because if we can do that, if we can show that if an entire generation has green eyes, the next entire generation will have green eyes, well, that means the next entire generation will have green eyes, the next one, the next one, the next one, the next one. That is induction. That's all you have to prove. So here's the idea on the proof. Let's go ahead and let n be any arbitrary / particular integer such that n is greater than or equal to 0. That's just what we want right there. And we're going to assume that it works for the iteration. Assume everyone in Dn has green eyes. All right. Now we're going to get to like the interesting part. Now we need to show from this, we want to show that everyone in Dn plus 1 has green eyes. And here's how I'll do that. I'll just consider any arbitrary thing, any arbitrary person in Dn plus 1 and show they must have green eyes. It has to happen. So let X be any arbitrary but particular person in Dn plus 1. So the children of Dn. I'll say note. Since n is greater than or equal to 0, yeah, since n is greater than or equal to 0, and y in Dn plus 1, y has a parent in Dn, or sorry, X. X is a parent in Dn, call them Y. So the point is, since X is an arbitrary person in Dn plus 1, their parent will be in Dn. And the whole n greater than or equal to 0 thing, we only care about that is because if you happen to pick X to be Daniel Valvo, well, then I wouldn't have a parent in D because I'm on the top of the family tree. But because n is greater than or equal to 0, n plus 1 is greater than or equal to 1, so you know that this person we're picking is at least in the next generation down, so they're not going to be me. So X is a parent in Dn, call them dy, or call them y. Now note, by assumption, y has green eyes. Because y is in Dn, we assume everyone in Dn has green eyes. That's the assumption we want. That's the assumption we have going in. We'll prove that necessarily means everyone in D plus 1 has green eyes. So is having a parent with green eyes enough to say that X has green eyes?
No.
What else do we need?
Don't you need that they marry someone from, what was the fact? From the Southern Hemisphere?
Yeah, they need to have one parent in the Southern Hemisphere. At least one. So, we know they have green eyes. If we can show that Y has one parent in the Southern Hemisphere, then we're good. Well, this kind of breaks down into two cases. X. Note Y is from the Northern Hemisphere or the Southern Hemisphere. Case 1. Y is from the Southern Hemisphere. Thus, X has a parent from the Southern Hemisphere, Y, and a parent with green eyes, also Y. Hence, by fact B, I believe it was, Yeah, by fact B, X has green eyes. So if this parent happens to be from the southern hemisphere, then we're automatically done, right? Because that means that this parent had green eyes, the parent from the southern hemisphere. So by fact B, this kid X has a parent from the southern hemisphere with green eyes. Therefore, X also has green eyes. But we also have to look at the other case where Y is from the northern hemisphere. So what do we know then?
They marry someone from the southern hemisphere.
Exactly. Since Y is in D, right? Y is in D because Y is defined as a parent in Dn, called in Y. So Y is in Dn, so it's in the nth generation of the Van family tree, and so they're in D. So since Y is in D, and Y is from the northern hemisphere, Y will marry someone, let's call them Z, from the southern hemisphere. Thus, X has a parent from the southern hemisphere, Z. Because in this setup, if we're assuming that the person that Y married, Z, is also the parent of Y's child. We're not getting scandalous here. So the point is, if we're watching the northern hemisphere, then they must have married someone from the southern hemisphere, so their spouse from the south. Spouse from the south. That's awesome. They got a spouse from the south, therefore X is a parent from the south, Z. Further, X has a parent with green eyes, that being Y. Therefore, by fact B, X has green eyes. Right, since they have parents from, since they have a parent with green eyes, and they also have a parent from the southern hemisphere. So all we have left is the conclusion. Or I'll say, in either case, X has green eyes. So no matter if Y, this parent, is from southern hemisphere or northern hemisphere, X is going to end up having green eyes. So we have a conclusion for all n greater than or equal to 0, and for all x and dn, X has green eyes. Thus, for all x and d, X has green eyes as desired. Box. You guys can see that, sorry. Any questions? I hope this makes sense kind of when you see it out. But the big idea was to break it down into induction on the generation you're in. So the idea, the whole idea of induction is if you can get this far, is proving you can get this far, is proving you can get this far. Some people think of it, the analogy they use, like I like the dominoes analogy. Some people use a ladder analogy, where it's like you climb up a ladder, and it's like if you can get to this rung, you can get to this rung. It's like if you know if you can get from this rung, you can get to this rung, well then you can get infinitely high up if the ladder's high enough. Yeah, so the idea is this inductive step tells us that if the claim is true for n, it's true for n plus 1. If the claim is true for this generation, it's true for the next generation, meaning it'll keep being true for every generation. As long as we can show it's true for one, which you do in the base case. Right? time is it? We got 10 more minutes. Any more questions? How do you guys feel about this? Like,
Not good.
yeah. I wouldn't. Is shaking is shaking your head. Good or bad, Opera?
So do we have assignment 5, like written assignment 5, like included or not? Because that was, I believe, after.
Number 4.
I think that was not included because I asked you last time if we have contents from written assignment 5. You said not much.
What was your assignment 5 again? Let me.
For test number 1. So it's definitely included in test number 2. But do we have number 10?
Oh, weak induction. You have that strong induction.
Okay.
Yeah. So the stuff that we just did, honestly, the first proof we did with the summation, if you understand that, you're in a very good position for the test. That's about as hard as we get. This next thing, this thing with the generations I showed you, is a little bit harder, which I like. I like having the written assignments and things be a little bit harder, but I'd rather the test be a little bit easier. It's like putting a donut on a baseball bat and it's easier to swing. Although apparently that's a myth. But anyway, the point is, I like to think it works. So yeah, if you can understand the summation thing, you're probably good. If you can understand the generation thing, you're probably really good. I wouldn't get too caught up in it though. In the sense, like I think a lot of people want to overthink induction. Induction is just weak induction especially, it's just 2 steps, the base case and the inductive step. All you do in the base case, you show the claim is true for one of them, the first one. And all you do in the inductive step, I show if you can get to one, you can get to the next. And that is it. By one, I don't mean the first one. I mean, like if you get to a, if you can prove it for a step, you can prove it for the next step. Yeah, and that's really all it is. Like everything else, like the real meat of an induction proof is the inductive step, because that inductive step is different every time. Every time in that inductive step, you have to kind of prove something unique in a different way. You know, like the inductive step in the summation is very different than the inductive step in the generations one, because there's different proofs. But the point is, like I don't want anyone to miss points, but I would be delighted if everyone missed points on proving the inductive step rather than miss points on misunderstanding what the inductive step was. If we all understand what the inductive step is, I'll be so happy. Oh, but I'm sorry. We're gonna have yeah. Yeah. So we're gonna time 10. So you should be able to do 1, 2, and 3, but not. You don't need to be able to do 4 yet. That'll be on test 3. So 5 minutes. We got time for one more. Anybody have anything else? Any homeworks? Any lecture notes? Anything that confused you? Now's the time. Nothing confused you. I feel so good. I'm such a good teacher. You guys understand everything.
Written assignment 8, question number 3.
All right. I know a good one. Let's check that out. Written assignment 8. Question number 3. So what is that exactly?
The claim was for all real numbers A, B, C, if A less than B and C is positive, which is greater than 0, then CA is less than CB.
Yes. Yes, that's a good one. I like this one a lot. So there's a few different ways to do this. I'll show you the way that I was hoping you guys would do it, because that's the way that you actually learn the contradiction. So the claim is real simple. It says for all A, in the real numbers, and for all B in the real numbers. Actually, what was my exact claim? It said, yes. Is that true? Yeah. So, whoops. Where's my, here we go. So for all A in the real numbers, for all B in the real numbers, and for all C in the real numbers, plus, meaning the positive real numbers, if A is less than B, then CA less than CB. This is the claim. And this is a fact that you guys have been using for years, probably since like 10th grade or something like that, in algebra 2, inequality algebra, right? That you can multiply an inequality by both sides by a positive number, and it doesn't change the inequality. If A is less than B, CA will still be less than CB as long as C is positive. But why? And here's the idea behind that. The way I want you guys to prove it is, I'll do an aside real quick, is just kind of by showing that it wouldn't make any sense if it wasn't true. So that's what like basically a contradiction proof is. So let's go ahead and assume that A is less than B, and somehow, instead of this happening, the opposite happens. Let's say CA is bigger than or equal to CB, and show that's ridiculous, that can't happen. Well, if CA is greater than or equal to CB, what we can do there is we can't multiply and divide by both sides because it's exactly what we're trying to prove, right? So we can't use that yet. But we can subtract. So I'm going to do that. It's going to equal C. Actually, I'm going to go the other way. I'm going to say 0 is less than or equal. I'm going to say CA minus CB is going to equal to 0. And then you can factor a C. Now, if C times A minus B, so this is a real number, times another real number, if these two real numbers multiplied to something greater than or equal to 0, what do we know about C and A minus B?
That it is going to be a real number too.
It will be a real number as well. It's very true, Afra. But specifically, like think about what you know about like what happens when you multiply a positive by a positive or a negative by a negative or a positive by a negative. What are the options for C and A minus B to make them greater than or equal to 0?
You have to be either like both positive or both negative.
Positive or negative, right? This implies that either C greater than 0, A minus B greater than 0, or we can have C less than 0 and A minus B less than 0. Well, what's the problem with this? I claim this can't happen. Why?
C is greater than 0.
Yeah, C is defined to be positive. It's in the positive real numbers. So that can't happen. What's the problem with this? This one's more subtle. Maybe I'll write A minus B. If A minus B is greater than 0, that means A is greater than B, right? What's the problem there?
It contradicts what we assumed.
Yeah, we're saying the case where A is less than B. We're working in that case. So this also can't be true because we know that A is less than B. So if A is less than B and C is positive, there's no way CA is greater than or equal to CB. It just won't make sense. It doesn't work. It'll reach a contradiction no matter how you look at it. So therefore, CA must be less than CB. Because it just can't be greater than or equal to CB. And that's the proof. So real quick, the proof would go something like this. You'd say proof. Proof by contradiction. So note the negation of this guy, that there exists an A and R, there exists a B and R, there exists a C and R plus, such that, what's the negation of this?
CA is greater than CB, then B is less than A.
I'm glad you said that, Afra, because this is a very common thing people say. But we have to remember, this is not the case. No. The negation, what you just wrote down, was the contrapositive. But remember, the contrapositive is actually equivalent to the original statement. Remember, the negation of P implies Q isn't a conditional at all. It's not the converse, it's not the inverse, it's not the contrapositive. It's P and not Q. The negation of if P then Q is that P does happen, but Q doesn't happen. That's the only way if P then Q would be false. So negation is such that, that's a very important fact. I'm glad we went over that. Such that A is less than B and CA greater than or equal to CB. Because that's what that's the opposite of what this is saying, I guess. There exists a case where this happens. So we do proof by contradiction, and then assume for sake of contradiction that there exists integers A, B, and C such that C is greater than 0, A is less than B, and CA is greater than or equal to CB. Right? This is the opposite of the claim. The claim is saying for every integer A, B, and C, such as C is positive, then A is less than B will imply C is less than CB. The negation is that there exists one where this fails. There exists a A, B, and C, so the A is less than B, but CA is greater than or equal to CB. And so, we can just do the exact thing we did in the aside right here. So let's note that CA greater than or equal to CB. I'll say consider this. CA greater than or equal to CB. This implies CA minus CB greater than or equal to 0 by subtracting CB on both sides. And this is equivalent to, we can factor by factoring a C. And this is all we need. So now we have C times A minus B greater than 0. Then the lemma on the problem is exactly what Mia said about how either C's got to be bigger than 0 or A minus B's got to be bigger than 0. Then, by a lemma, C is going to equal to 0, and A minus B is going to equal to 0, or C is less than equal to 0, A minus B is less than equal to 0. Now I'll say this breaks into two cases. Case 1, let's look at this case first. C greater than or equal to 0, and A minus B equals 0. Thus, by adding B to both sides, A is going to equal to B. But this is a contradiction. Contradiction, we assumed A is less than B. So A can't simultaneously be greater than B and less than B makes no sense. That's a contradiction. Now, case 2 is the even simpler one. C is less than or equal to 0, and A minus B less than or equal to 0. This is already a contradiction. Because we assume C is greater than 0, so it can't be less than or equal to 0. I'll say contradiction. C is assumed to be greater than 0. So, in either case, we reach a contradiction. And then this is just like the Gardner situation. In either case, we reach a contradiction. So what that means is if we reach a contradiction, that means our assumption had to be false. Our assumption could not have been true. It does not gel with the rest of the facts of math. So thus, our assumption must have been false. So if you start from a premise and you use valid logic to reach an incorrect conclusion, what I talked about before, way a long time ago, that means your premise must be false. Therefore, so the premise is false, the opposite must be true. And the premise is just saying that our claim is false. It's just assume the negation of our claim. So therefore, the claim must be true. And that's that. Does it make sense when you see it like that? Good. Good. Because again, I think this is harder than what you'll see on your tests and stuff. So a little bit. It's reaching a little bit.
Because I was going through the solutions and I didn't understand.
Do you understand?
I mixed up the contrapositive and the contradiction.
Yes. Oh, the contrapositive and the negation up here?
No.
Yeah. So the contrapositive of P implies Q is not Q implies not P. The negation is what we want here. So this is not the contradiction. This is the negation. Now, contradiction is a proof technique, and the contradiction proof technique, you start by assuming the negation, just to get the vocabulary there. But we are 8:10, so I think I'm going to shut it down. Does anyone has any pressing questions to ask me? Okay, well, Mia Afra, thanks for showing up. I hope this helps. I hope you guys absolutely annihilate that test tomorrow. And email me if you have any more questions.
Thank you.
You're
Thank
welcome.
you.
Or night, whatever it is these days. It gets dark so early. Who knows? Bye.
Bye.